But let's look at the next one now. Question number 6. Okay, now it says Freddy has 2 bags of marbles. Bag X contains 7 red marbles and 3 blue marbles. Bag Y contains 4 red marbles and 1 blue marble. Freddy chooses one of the bags at random. A marble is removed at random from that bag and not replaced. That means you're not putting that marble back in the bag. Okay. A new red marble is now added to each bag. A second marble is then removed at random from the same bag that the first marble had been removed from. Draw a tree diagram to represent this information, showing the probability on each of the branches. Now, that's a fairly complicated looking scenario. So let's break it down. So go in sequence. When you're drawing a tree diagram, do things sequentially. Do them step by step. What's the first thing that's happening? The first thing that's happening is she's choosing one of the bags at random. Okay, one of the bags is being chosen at random. Now, if it's being chosen at random, that means the probability of choosing X or Y, that's basically equal. So you have 2 possibilities. First of all, you could either choose X or Y. They have equal probabilities. So this is 0.5 and this is 0.5. Because choosing randomly. A marble is removed at random from that bag. So whichever bag is chosen, one marble is removed from that bag and not replaced. Okay, so if it's the first bag X, what are the 2 possibilities? When a marble is taken at random, what could those 2 colors be? It could either be red or it could be blue. What's the probability of having a red marble? 7 over 10. The total number is 10. 7 out of 10. That's 0.7. And for blue marble, it will be 0.3. And in case it was a yellow marble, in case it was the bag Y first, you could have a red marble or a blue marble. The probability of red marble is 4 out of 5. That's 0.8. And the probability of having a blue marble is 0.2. This happens in the second step. So this was the second step that we looked at. A marble is removed from the bag and not replaced. What's happening next after this? The next thing that's happening is a new red marble is now added to each bag. Okay, so now they're adding a red marble to each bag. There's no probability involved here, so we're not going to have any branch for this. It's just that initially we had 7 red marbles and 3 blue marbles and 4 red marbles and 1 blue marble in each of those in both of those bags. Now, after this first step, one new red is added. Then what happens? A second marble, after red marble is chosen, a second marble is then removed at random from the same bag that the first marble had been removed from. Okay, so if the first marble was removed from bag X, now you remove a second marble from bag X again. There are 2 possibilities here. Similarly, if the first marble was removed from bag Y, again, you have 2 possibilities here. You've got 2 possibilities here. For the second time you choose a marble, again, you've got 2 possibilities for each of these cases. You could either have a red marble or a blue marble, red marble or a blue marble, red, blue, red, blue. Now, keep in mind the number of marbles that we had in the beginning and what's happening at this particular point. Now, in fact, it might make it easier to figure out what's happening in the next step if you write these values as fractions instead, so that you know the actual number as well. So red marbles were 7 initially, so we can write them as 7 over 10, and this was 3 other. So total balls were 10, 7 were red, 3 were blue. Okay, so writing this as fraction would make it easier to understand what to do in the next step. This is 4 over 5 because we had 4 out of 5 red marbles, and then here it was 1/5. Now think about it. If the first time marble R was taken from box X, how many marbles are we left? How many red marbles are we left with at this point? 6, 3. 6 red and 3 blue. However, a red marble is added here, so it becomes 6 plus 1. So what's the probability of getting a red marble again? It's again going to be 7/10. And what's the probability of having a blue marble again? That is again going to be 3/10, because the total number becomes the same as before once a red marble is added, because you removed 1 red and they placed 1 red back inside. This is what you get in the first 2 branches. If, however, from bag X the first time, a blue marble was taken. The first time the blue marble was taken, what's the number of red marbles and blue marbles at this point? 7 red and 2 blue after a blue is taken out. And then a new red marble is added. So the number of red marbles becomes 8 now. So the second time, the probability of getting a red marble is 8/10. The probability of getting a blue marble is 2/10. That's what you get in this case. Okay. Let's move on. See what happens in box Y now. When you take a red marble the first time, what's the number of marbles for each of them? How many red do we have? How many blue do we have? After taking 1 red out, we had 4 initially. Now we're left with 3 red and 1 blue. And you add 1 red again, so that's 3 plus 1, 4. So probability of having a red marble again is still 4/5, and this is 1/5. In the other case, however, when a blue marble was taken the first time, how many red marbles do you have? How many blue marbles do you have at this point? You had 4 left of red marbles and 0 blue marbles. You add 1 more, it becomes 4 plus 1. 5/5. The probability of having a red marble the second time is basically 1, because there are only red marbles in the box now. There's no blue marble. The probability of having a blue marble is 0. So this basically means you can write it like this if you want: 5/5 and 0/5. Right? So that's 1 and 0. This is what the tree diagram looks like. Okay. Now let's move on. That was part A. I hope that makes sense, right? Any problems? Now it says, find the probability that both of the marbles removed from the bag are the same color. Okay, now that you've made that tree diagram, I think the rest of it is not going to be very difficult now, because the rest is going to be a standard probability question. It says, find the probability that both of the marbles removed from the bag are the same color. Now, what are the possibilities that we have? It could either be red, red, blue, blue, red, red, blue, blue. You just add all of these probabilities, and that's going to give you the result. Now, what's the first case? That you choose bag X, pick up a red marble the first time, pick up another red marble the first time. Let's see what that gives us. It's going to be 0.5 into 7/10 into 7/10. That's the first case. Okay. That's basically this case. This. That you choose X, box X, and you choose 2 red marbles from that. And then the next possibility is you select box X, and from that box X, you choose 1 blue marble and the second blue marble. 𝗨𝗲𝗿, let me come back to your question in a moment. So if we have both blue marbles taken out, what does that give us? That's 0.5 into 3/10 into 2/10. That's another possibility of getting same colored marbles. Then if you chose box Y, you could get red grid from that. What does this give you? 0.5 into 4/5 into 4/5. And then finally, from box Y, you could choose B and B as well. What does that give you? That's going to become 0 because you have a 0 in there. 0.5 into 1/5 into 0. And now you just evaluate all of these cases and add them up together. That is going to give you the final result. You can see what this turns out to be. 7/10 into 7/10. What's that? Into 0.5, in fact. 0.5 into 0.7 into 0.7. The first one is 0.245. I recommend you evaluate each one of them separately as well, but because often there is a condition probability part later. Yeah, so write down each of those probabilities separately. They will help you in the next parts. Okay, what's the first one? The first one is turning out to be 0.24. Okay, then 0.5 into 0.3 into 0.2, that's 0.03. 0.5 into 0.8 into 0.8, that's 0.32, and this is 0. You just add all of these cases, and that gives you the result. Okay, because it could be any one of those three cases. So basically, now add those cases, 0.245. You've done this calculation on the tree. You have shown that calculation on the tree, or you can either show this calculation here, or in this space, you have to show calculation somewhere so that the examiner can check your working. It's a 4-mark question. You should not write the answer directly. You need to show this working somewhere, that you're multiplying this. Okay, this needs to be shown. 0.245 plus 0.03 plus 0.32, and that's going to give you the result. What do you get? 0.245 plus 0.35, and that's 0.595, right? That's 0.595. That's what we're getting from this. 0.595. That's the probability that both of the marbles removed from the box are the same color. Okay. No, so the question is, can we show the working above the question? That means you can show the working here. If you're showing the working above, you should show that along with the tree. But if you have to write it separately, then it's better to write in the space that's given here. You can either show your working along with the tree, and that's okay. But if not with the tree, then you should write here. Don't write in this space. Okay. All right, so that's 0.595. Now it says, find the probability that bag Y is chosen given that the marbles removed are not both the same color. Okay, now what does that mean? Probability that bag Y is chosen, probability that bag Y is chosen, given that both marbles are not the same color. That's what you have to find out. Now, how do you do that? It's conditional probability. In the numerator, you would have the probability of both of these things happening together, probability of choosing Y and both not being the same color. That's what you're going to have in the numerator. And in the denominator, you have what is given. What's given? Not being the same color. Both not the same color. That's the probability that we're looking for. What about the denominator? Both not the same color. We have found the probability of both being the same color. That's 0.595. So what's the probability of both not being the same color? We just subtract this from 1, right? So the denominator is pretty straightforward to calculate, or you could do it directly as well. You could find this case, this case, this case, and this case, and add all of those 4 probabilities. And that will give you the same as this, as what you would get by subtracting this number from 1. So in the denominator, so this probability, both not being the same color, this is basically 1 minus 0.595. The probability that you've calculated in the first part, subtract that from 1, and that will give you this probability. Now, what about the numerator? In the numerator, you want both of these things happening at the same time. That y should be chosen, and both of them should not be the same color. Now, when y is chosen, let's go back there here. When is y chosen? Here. When are both not the same color? It's either this case that you choose y and you have first red and then second blue. That's one possibility. Or you choose y and you have first blue and second red. These are the 2 cases that you're going to have in the numerator there. What are these 2 cases? Let's evaluate them. 0.5 into 4/5 into 1/5. And the second one is 0.5 into 1/5 into 5/5. These are the 2 cases where both of those things are happening together, that you are choosing y and both are not the same color. 0.5 into 0.8 into 0.1, 0.2. That's giving me 0.08. 0.5 into 0.2 into 1, that is 0.1. These 2 cases together are going to be in the numerator here. So in the numerator, we have 0.08 plus 0.1, right? That's the case that we get here, 0.08 and 0.1. Let's evaluate this. What do we get? 1.08 divided by 0.405. And that's giving me something that's wrong. Let me check this again. Okay, sorry, I wrote the wrong value there. 0.1 plus 0.08, that's 0.18. 0.18 divided by 0.405, that is giving me 4/9. Right, I was getting something greater than 1 earlier. This is 4/9, and that's 0.444 in decimals. You can leave it like this. That's 4/5. That's what we were looking for. First part, that's all that you have to do here. In the second part, you have to find expected value and variance. For that, you can just use the formulas. Okay. All right. Let's move on to the next one. So the next question that you're asking, that's most of you are asking about, that most of you are asking about is question number 2. Let's have a look at that now. It says a sports event is taking place for 4 days, beginning on Sunday. The probability that it will rain on Sunday is 0.4. Okay. So it's for 4 days, starting on Sunday. Probability of raining on Sunday is 0.4. On any subsequent day, the probability that it will rain is 0.7 if it rained on the previous day, and 0.2 if it did not rain on the previous day. Okay, probability is 0.7 if it rained on the previous day, and 0.2 if it did not rain on the previous day. Find the probability that it does not rain on any of the 4 days of the event. Okay, so probability of not raining on any of the 4 days. What's the probability of not raining the first day? 0.6, right? If probability of raining is 0.4, probability of not raining will be 0.6. And then if it did not rain the previous day, the probability of raining on the next day is just 0.2. So what's the probability of not raining the next day as well? That will be 1 minus 0.2, which is 0.8. And then for the third day as well, 0.8. And then for the fourth day as well, 0.8. You would just multiply all of these probabilities and see what that turns out to be. Let me calculate this 0.6 into 0.8 into 0.8 into 0.8. That gives us 192/625. In decimals, that is 0.3072. Okay, that's the first part. Any problem with this? Really straightforward, right? Now it says, find the probability that the first day on which it rains during the event is Tuesday. Probability that the first day on which it rains is Tuesday. That means, what's the probability that it does not rain on Sunday? So no rain on Sunday, and then no rain on Monday, and then rain on Tuesday. We don't care what happens after that. We're just talking about Tuesday. So the first day of raining is Tuesday, okay? Now, that might actually remind you of something. Probability of first success, getting our first success in a particular outcome. Remember, for geometric distribution, we used to use that. However, if you think about this, we can't treat it as geometric distribution because the conditions for geometric distribution are not fulfilled here because the probabilities are changing. If it rains one day, the probability of raining the next day is different as compared to if it did not rain on a day, the probability of raining the next day would change because of that. Since the probabilities are changing, we can't use geometric distribution here. That would not work. Okay, so keep that in mind. Even though we're talking about first success here, probabilities do not remain constant. So the conditions for geometric are not fulfilled. Those formulas do not work here. So we just have to do it logically like we did in the first part. Probability of not raining the first day. Probability of raining the first day was 0.4. What's the probability of not raining? 0.6. If it did not rain the first day, what's the probability of not raining the next day as well? Probability of raining was 0.2. Probability of not raining would be 0.8, just like in the previous part. But now, what's the probability that it rains the next day? Now, the previous day, it has not rained. Now, given that it did not rain on the previous day, what's the probability of raining the next day? 0.2. So you multiply this by 0.2, and that should give you the result. You can see what this turns out to be. 0.6 into 0.8 into 0.2. And that's giving me 0.096. That's part B of this. All right. Make sense? Let's have a look at the next one. Now it says, find the probability that it rains on, we don't care about the fourth day. They're saying, find the probability that the first day on which it rains during the event is Tuesday. It doesn't matter what happens after that, right? We don't care about them. Now, it is possible that it rains on Wednesday or it does not rain on Wednesday, but we don't care, right? Because that's not what we're looking for. Find the probability that it rains on exactly one of the 4 days of the event. If you take both possibilities, you just add both of them up and you will get the same result, right? So you can do that. Okay, now find the probability that it rains on exactly one of the 4 days of the event. What does that mean? Exactly one of the 4 days. Now, it could be any one of those 4 days. So there are 4 possibilities now. It might be that it rains the first day and then it does not rain. And then it does not rain and then it does not rain. That's one possibility. You can't multiply this by the 4 possibilities. Why? Because all of those possibilities are different. You'll have to calculate all of them separately. Rain, no rain, no rain, no rain. That's one possibility. Then you could have rain, sorry, no rain, rain, no rain, and no rain. That's the second possibility. Another possibility would be no rain, no rain, rain, and no rain. And then finally, no rain, no rain, no rain, and rain. These are the 4 possibilities you could have. You could try drawing a tree diagram for this, but that will become too big. So that's why it's going to be quicker and easier to think of it like this. If you were to draw a tree diagram, it would be rain, no rain, and then rain, no rain for each of them. And then for each of them further, you have 2 possibilities. And then for each of them further, you've got two possibilities again. So it becomes a tree diagram in which at the end you have 16 branches. You could do it that way, but that's going to take too long. So that's why we just think of it logically like this, okay? And these are the four options through which you could have exactly one day on which it rains out of the four. Now, what are the conditions that we're given? The first time, probability of raining is 0.4. So the first time, the probability of raining is 0.4. Probability of not raining the first time is 0.6, 0.6, 0.6. That is for just the first day, for Sunday. What happens after that? After that, if it rained the previous day, let me write that here. If it rained the previous day, the next day, probability for raining the next day would be 0.7. And probability of not raining would be 0.3. And if it did not rain the previous day, the probability of raining the next day would be 0.2. And the probability of not raining the next day would be 0.8. So keep that in mind. Keep those conditions in mind. Okay. Now, if it rained the previous day, what about probability of not raining the next day? 0.3. And now, what about the next day? It did not rain the previous day. Now the next would be 0.8 from here. We've got 0.8, and then again 0.8. And then the next condition, next case, no rain the first day, that's 0.6. What's the probability of raining given that it did not rain the previous day? That will be this one, 0.2, right? And then what's the probability of not raining given that it rained the previous day? That's this, 0.3. And then given that it did not rain the previous day, what about the next one? This will be 0.8 from here again. That's the second case, okay? We multiply these, and that's going to give you the probabilities in the first two cases. Now, what about the third case? So can somebody please do this calculation for me as well? Okay. If it did not rain the first day, what about not raining the second day? 0.8. And then what about raining the next day? 0.2. And then not raining again? 0.3. And then it did not rain the first day, and still it did not rain the second day as well. 0.8, and then 0.8 again, and then raining after not raining the previous day. That will be here, 0.2. This is what we get. These are the four cases that we get. What we have to do now is we have to add all of them up, and that will give us the result. Okay, so what do we get? 0.4. So anyone who has done the calculations, 0.4 into 0.3 into 0.8 into 0.8, that's giving me 0.0768. 0.6 into 0.2 into 0.3 into 0.8. Now, looking at this question, it did not look that complicated, to be honest. But now this part C was fairly complicated. 0.0288. Okay. And then 0.0288 again, because these are the same numbers. Yeah, 0.0288. And then finally, 0.0768, because these two are also the same. They don't look the same. Yeah, but 4 into 3 and 6 into 2, that's the same thing. That's 0.0768. Okay. And then you add all of them up. Total probability. You add all of those numbers, and you're telling me this turns out to be 0.2112. 0.2112, that's the total that we get. Okay, so that's how you find this probability. Okay, that thing throws two ordinary phase 6-sided dice at the same time and notes the numbers on the uppermost faces. The events A and B are defined as follows. The sum of the two numbers is less than 6. The difference between the two numbers is at most 2. Determine whether or not the events A and B are independent. Okay. Now, first of all, remember the condition that we've got for independent events. We need to remember that condition. If two events are independent, this has to be true. The probability of their intersection, that means probability of both of them happening at the same time, that should equal probability of A multiplied by probability of B. That's the condition for two events being independent. So you need to check this. You need to find the probability of A, you need to find the probability of B and the probability of their intersection, and then check if these two things are equal. Okay, now how do we do that? Let's think about the first event. So there are two dice that we're throwing. What's the probability of the sum of the two numbers being less than 6? Now, one possibility is that you make that 2D table, addition table, right? For figuring out this, or you can just think of it mentally. Let me see how many cases we could have in this case. 1, 1, 1, 2, 1, 3, 1, 4. Yeah, so you can list down as well. If you want, you can make that two-dimensional table, addition table. If you want to make things, if you think that will make things simpler for you, you can do that. Or you can just list down these cases directly as well. So sum of the two numbers is less than 6. What are the possibilities you could have for them? Now, if you want to list them down, the way to do it is like this. You start in one structured way that you say, okay, what if the first dice gives you number 1? Then what are the possibilities for the second dice? So keep the first dice number fixed. So that's 1. With the first dice showing 1, what are the possibilities for the second dice? You could have 1, 1. You could have 1, 2, and all the way up to 1, 5. All right. In fact, 1, 4, because it's less than 6. Let's write them down. 1, 3, 1, 4. These are the 4 cases when the first dice shows 1 and the second dice shows 1, 2, 3, 4. Okay. We can't have 1, 5 because that will be equal to 6. We don't want that. Okay. Now, the next possibility could be that the first dice has 2. With 2, you could have 1, 2, and 3. And then with 3, you can have 3, 1, 3, 2, and that's it. And then finally, with 4, you can have 1. These are the possibilities that you have for event A. All right. What's that probability? Can we write them down now? Since we're throwing 2 fair dice, the total number of possible outcomes, that is 36. What are the outcomes that satisfy this condition? There are 10. How many outcomes are there? 10. Let's write that here. Probability of A, that's 10 out of 36. That's the probability of A. Okay. Now, what about B? The difference between the two numbers is at most 2. So now we need to think about the differences between numbers. It should be at most 2. That means it could be 0, it could be 1, it could be 2. Again, you could make a table that lists down all the differences that is possible. Or you could just think of it logically, just like we did for A. So you'd have to make another table for this if you wanted to do that. And that's okay, you could do that. The difference has to be at most 2. So what are the possibilities? Now, let me list them down. With 1, what possibilities could you have? For the second dice, you could have 1, 1. You could have 1, 2. Or you could have 1, 3. So with 1, you've got these 3 possibilities. These will be a lot of cases actually, but okay. 2, 1. 2, 2, 2, 3, and 2, 4. With 3, you'll have 5 cases. Let's do it the other way around. That might make things simpler. Or let's make a table for this. In this case, since these are too many cases, it will be easier, I think, to make a table in this case. Let's do that. Because it will be more than half the cases in this case. Let's make a table. So that will be quicker in this case, I think. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's make a difference table and see what we get for that. All right. So calculate the differences. So from one of them, subtract the other. Let's say this is first dice and this is the second dice. Okay. So what do we get from this? 0, 0, 0. On the diagonal, it's going to be all zeros, right? And then 2 minus 1, that's 1, 2, 3, 4, 5. You have 1, 2, 3, 4. 1, 2, 1, 1, 2, 3, 3, 2, 1, 1, 2, 4, 3, 2, 1, 1, 5, 4, 3, 2, 1. Now, this is going to be less prone to error if you list them down like this, because there are too many cases. If you try listing them down, it's more probable that you end up missing a possible case. So it's better to make a table like this in this case. Okay, that will be less prone to error. So now let's look at the cases where the difference is at most 2. So you've got these 3 cases, these cases, and these cases, and then these cases, then these and these. All right. So these are the cases when the difference is at most 2. Let's count them. How many cases are these? 1, 2, 3, 4, 5, 6, and then 6 on the other side. Subtract 12 from 36. That's 24 cases. 24 out of 36. This is what we're getting for the probability of B. Okay, so we got the probability of A and the probability of B. Now we also need the probability of their intersection. Intersection means when are both of those things true? That means that the sum of the numbers is less than 6 and the difference is at most 2. When are both of those things true? So what are the common elements between these two cases? Okay, let's figure them out. What are the common cases? 1, 1, it's appearing in both of them. This is common, right? 1, 1 is appearing in both of them. 1, 2. So what you can do is you can think of it like this. These are all the cases. I'm sorry. These are all the cases that satisfied the first condition that were part of the event A. How many of these also have the difference at most 2? How many of these cases have a difference that is at most 2? Let's just count them, because they will be the ones that are common then. This is one case, another case, 3, and then you have 4, 5, 6, 7, 8. Yeah, so you've got 8 cases here that are common between the two events. These green cases satisfy both conditions. Here the number is less than 6, the sum of the numbers is less than 6, and the difference is at most 2. So if you had to write down the probability of the intersection now, probability of A intersection B, out of 36 cases, there are 8 cases that are common. This is the intersection. Okay. This is what I highlighted in green there. Make sense? And now we need to check if this condition holds true or not. Let's check that now. Eight over 36. And on the other side, we've got 10 over 36 into 24 over 36. Let's see what they simplify to. 8 over 36. That simplifies to 2 over 9. Let's see if they're equal or not. On the other side, we've got 10 over 36 into 24 over 36, and that's giving me 5 over 27. So that means they're not equal. Since they're not equal, we say probability of A intersection B is not equal to probability of A multiplied by probability of B that means A and B are not independent. They're not independent. Okay. If both of these values were the same, then we would say that they are independent. In this case, they are not independent. Is that okay? Make sense? So this is the condition that we need to remember for this. For events to be independent, probability of A intersection B is equal to probability of A multiplied by probability of B. In this case, that was not true. They are independent of each other, of course, yes. They're not independent in this case. So if A happens, it has an effect on B. If B happens, it has an impact on A. Okay, they are not independent. Okay, now it says find probability of B given A complement. What does that mean? Probability of B given A complement. How do we think about this? Remember the formula? Probability of A given B, that is given by probability of A intersection B divided by probability of B. So in the numerator, we've got the event in which both the things happen together. In the denominator, we've got the probability of what is given. Okay. Let's translate that to these events. That means probability of B intersection A dash divided by probability of A dash. That is what we are looking for. Okay. In the numerator, we've got B and A complement. That B happens and A does not happen. In the denominator, we've got the event that A does not happen. Now we've listed down all the cases in the first part. Let's find out the denominator from that. Probability of A not happening. What was the probability of A happening? That was 10 out of 36. What's the probability of A not happening? 1 minus this number, which is 26 out of 36. That's what you have in the denominator. That's the probability of what is given. Okay. In the numerator, it's B and A complement. That B is true and A is not true. How do we think of these cases where B is true and A is not true? We have 24 cases in which B is true in total. We have 24 cases in total in which B is true. Out of these cases, when is A not true? We know that A is true in 8 of these cases. So A would not be true in the remaining cases. 24 minus 8, that is 16. In 16 of these cases, in 16 out of these 24 cases, B would be true and A would not be true. So in the numerator, we have 16 out of 36 because of that. Let me show that to you here in the yellow part. In the yellow part, in these yellow highlighted parts, B is true, right? B is happening here in these yellow parts. In these yellow shaded numbers, we are saying the difference between the numbers is 2 at most. Out of these, how many have the sum of the numbers not less than 6? Right? A should not be happening. That means the sum should not be less than 6. Where is the sum not less than 6? 3, 3. So as soon as we go beyond this point, when you have 1 here and 5 here, so basically this point, and then 2 and 3, that's here, and then 3 and 2, that's here, and then 4 and 2, that's here, and that's here. All the numbers in this region, let me check again. 4 and 2, that's 6. 3 and 3, that's 6. 2 and 4, that is 6. And then 4, 4. Yeah. I think we're missing one number here somewhere. Because that was 16 when we calculated it that way. Are we missing something? 1, 2, 3. Yeah, that's okay. So all the numbers above this yellow boundary that I've drawn, these numbers, you can see the sum of the corresponding numbers on the dice that is less than 6. And for all of these parts below, the sum of these numbers corresponding on these axes, that is either 6 or more than 6. How many of these are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's another way of thinking about this, although I think that's going to make things a bit more complicated. You can just think of it directly. There are 24 cases in total for event B. Out of them, this is the intersection. You just subtract that from that. So basically, from 24, you're saying subtract the intersection. That's 8 out of 36, and that gives you 16 out of 36. That's what you have in the numerator. All right. And that will give you the result. You can see what that turns out to be. 16 over 26. And that should give you 8 out of 13. That's the result. Does that make sense? Any problems with this? Can't we just add B and A dash? This is intersection. Intersection means what's common between them. So how can we add them? We are looking for intersection of them, right? Where B and A dash both are true. So we're just looking for common things between them when both conditions are met. No, we can't multiply as well. We can't multiply. Multiplication is only possible in independent events. And we proved in the first part they're not independent. Yes, A dash means A is not happening. Yes. We can't multiply. Multiplication is only possible when the events are independent. We can't figure out this by multiplication. We have to figure out from the cases that we've just done. We have to count. There's no other way. Multiplication will not work. You can't say you multiply probability of B and probability of A dash. That will not work. That only works for independent events. These are not independent. We already proved that in the first part. Question number 5. Marco has 4 boxes labeled K, L, M, and N. He places them in a straight line in the order KLM and KLMN with K on the left. So they're placed like this. There are 4 boxes. Let's say they are like this. Box K, L, M, N. These are the 4 boxes that we have. Now he has 4 colored marbles, red, green, white, and yellow. He places a single marble in each box at random. Events A and B are defined as follows. Okay, इसको ऊपर लिख लेते हैं इनफैक्ट बॉक्सेस की लेबलिंग ये है KLMN. इनके अंदर अब क्या इनपुट करें? R, G, Y, W और yellow. R, G, W, yellow. ये 4 कलर्स इसके अंदर इनपुट करें. Event A is that the white marble is either in box L or box M. And event B is that the red marble is to the left of both the green marble and the yellow marble. What we have to do is determine whether or not events A and B are independent. Okay, whether A and B are independent. Independent events में क्या होता है? Remember the condition that we have for that. Probability of A intersection B, that is equal to probability of A मल्टीप्लाइड बाय प्रोबेबिलिटी ऑफ पी। तो आपको ये चेक करना है क्या ये चीज होल्ड करती है कि नहीं करती है। अगर ये दोनों इक्वल है तो फिर ये इंडिपेंडेंट होंगे, अगर ये दोनों इक्वल नहीं है तो फिर ये इंडिपेंडेंट नहीं होंगे। तो हमें ये दोनों प्रोबेबिलिटीज निकालनी है और उनको चेक करना है कि वो इक्वल है या नहीं है। लेट्स डू दैट। इवेंट ए इज द व्हाइट मार्बल इज इन आइदर बॉक्स एल और बॉक्स एम। अच्छा देखें इसके कितनी पॉसिबल आपके पास अरेंजमेंट्स हो सकती हैं इन 4 कलर्स की। देयर आर 4 डिफरेंट कलर्स, 4 आपके पास बॉक्सेस हैं। कितने वेज में इनको अरेंज कर सकते हैं? 4 फैक्टोरियल वेज में अरेंज कर सकते हैं, राइट। सो टोटल अरेंजमेंट्स आपके पास कितनी है विदाउट एनी रिस्ट्रिक्शंस? टोटल अरेंजमेंट्स आर 4 फैक्टोरियल व्हिच इज 24। 24 वेज में आप इनको अरेंज कर सकते हैं इन बॉक्सेस में, इन 4 कलर्स को। नाउ इवेंट ए में कंडीशन क्या है, प्रोबेबिलिटी आपने क्या फाइंड करनी है कि जो व्हाइट मार्बल है वो एल बॉक्स एल में होना चाहिए, एम में होना चाहिए। तो व्हाइट मार्बल या तो यहाँ पर आ जाए या फिर यहाँ पर आ जाए, ये 2 पॉसिबिलिटीज हो सकते हैं। अच्छा अगर व्हाइट मार्बल को हम बॉक्स एल में प्लेस कर देते हैं, अगर व्हाइट मार्बल को बॉक्स एल में प्लेस कर देते हैं तो कितनी आपकी अरेंजमेंट्स होगी बाकी मार्बल्स की? 3 आपके पास बाकी मार्बल्स हैं और 3 बॉक्सेस हैं, उनकी अरेंजमेंट्स कितनी होगी? 3 फैक्टोरियल। अगर व्हाइट को हम यहाँ पे प्लेस करते हैं सेकंड के अंदर, let me actually make some space here so I could show that here. टोटल अरेंजमेंट्स तो आपको पता चल गई। एक केस आपका ये होगा व्हाइट वाले के अंदर, और दूसरा केस क्या हो सकता है कि एक ये कि व्हाइट यहाँ पर आ जाए, दिस इज वन पॉसिबिलिटी, एंड द सेकंड पॉसिबिलिटी इज बॉक्स ए के केस, इवेंट ए के केस में कि डब्ल्यू जो है वो इधर आ जाए और बाकी फिर आपके जो 3 कलर्स हैं उनमें से कुछ भी बाकी बाकी सब में आ सकता है। अब फर्स्ट वाले में कितनी पॉसिबिलिटीज हैं? 3 फैक्टोरियल। और सेकंड वाले में कितनी पॉसिबिलिटीज हैं? 3 फैक्टोरियल। इनको ऐड कर लें, 6 + 6 आपके पास टोटल 12 केसेस बनते हैं जो इस कंडीशन को सेटिस्फाई करते हैं कि व्हाइट या तो आपका सेकंड बॉक्स में आ रहा है एल में या फिर थर्ड में आ रहे हैं। उनके बाकी तीनों को प्लेस करने के आपके पास फिर तीनों के अंदर 3 फैक्टोरियल वेज होंगे। बाकी आपके पास क्या है? और जी वाई, उनके 3 फैक्टोरियल वेज होंगे दोनों के अंदर। सो प्रोबेबिलिटी ऑफ ए क्या होगी फिर? कितने केसेस में कंडीशन को सेटिस्फाई करते हैं? 12 आउट ऑफ हाउ मेनी? 24। द प्रोबेबिलिटी ऑफ ए टर्न्स आउट टू बी 1/2। ओके, ये पहला वाला केस तो हमने फिगर आउट कर लिया। अब दूसरा केस क्या है? द रेड मार्बल इज टू द लेफ्ट ऑफ बोथ द ग्रीन मार्बल एंड द येलो मार्बल। रेड मार्बल जो है वो ग्रीन और येलो दोनों के लेफ्ट में होना चाहिए। तो अब इसमें क्या पॉसिबिलिटी हो सकती है? लेट्स थिंक अबाउट दिस। अगेन वी हैव दोस 4 बॉक्सेस K, L, M and N. अब रेड मार्बल कहाँ पर हो सकता है? अब देखिए रेड मार्बल अगर मैं यहाँ पे प्लेस कर दूं, अगर मैं रेड मार्बल यहाँ पे प्लेस कर दूं जस्ट एज एन ऑप्शन, अब क्या ये पॉसिबल है? ग्रीन और येलो दोनों राइट पर आने हैं, मेरे पास तो स्पेस ही एक है राइट साइड के ऊपर, तो राइट साइड पे तो पॉसिबल है। तो रेड मार्बल यहाँ पे भी नहीं आ सकता और यहाँ पे भी नहीं आ सकता, ये दोनों पॉसिबल केसेस नहीं है। तो या तो रेड जो है वो इधर आएगा, एल में आएगा, ताकि राइट साइड पे बाकी दोनों आ जाएंगे, फर्स्ट केस हो गया। अगर रेड यहाँ पर आता है तो इसके लेफ्ट साइड पे क्या रखना पड़ेगा? फिर लेफ्ट साइड पे इसके ये वाला केस रखना पड़ेगा, व्हाइट रखना पड़ेगा, बिकॉज ग्रीन और येलो राइट पे होना चाहिए ना, तो लेफ्ट में मुझे व्हाइट रखना पड़ेगा। अब राइट साइड पे क्या ऑप्शन होगी? ये तो फिक्स्ड हो गए, ये 2 स्पेसेस मेरे पास रहेगी, उनमें 2 आपने प्लेस करने हैं, या येलो या ग्रीन। ये कितने वेज में अरेंज हो सकते हैं? 2 फैक्टोरियल वेज में। तो फर्स्ट केस में आपके पास 2 पॉसिबल केसेस बनते हैं, ठीक है। अच्छा दूसरा केस क्या हो सकता है कि रेड को आप यहाँ पे प्लेस कर दें। अगर रेड को यहाँ पे प्लेस कर दें, अब बाकी तीनों में कोई जैसे मर्जी अरेंज हो, इट डजंट मैटर, बिकॉज वो कंडीशन सेटिस्फाई होगी, ग्रीन और येलो राइट पे आ रहे होंगे, उनमें कोई कंडीशन नहीं रहेगी। फिर बाकी 3 कलर्स को अरेंज करने के कितने वेज हो जाएंगे? 3 फैक्टोरियल। इनको ऐड कर लें, आपके पास क्या आता है? 2 + 6 विच इज 8। तो इवेंट बी की प्रोबेबिलिटी आपके पास कितनी होगी फिर? इवेंट बी की प्रोबेबिलिटी हमारे पास आ जाएगी 8/24। What's the probability of event B? 8/24. And that turns out to be 1 out of 3. अब हमें देखना है इनका इंटरसेक्शन। इन दोनों में कॉमन क्या चीज है जहां पे दोनों कंडीशंस मीट हो रही हैं? ये हमने ए और बी के अलग अलग तो निकाल लिया, ए के भी दोनों केसेस निकाल लिए, बी के भी दोनों केसेस निकाल लिए। अब क्या इनमें कोई ओवरलैप है? दैट इज व्हाट वी नीड टू फिगर आउट। ओके, अच्छा अब देखते हैं ओवरलैप हमारे पास क्या आ रहा है। दोनों प्रोबेबिलिटीज अलग अलग तो निकाल ली, क्योंकि वो हमने ये इस इक्वेशन में चेक करना है इनपुट करके, तो हमें इंटरसेक्शन की प्रोबेबिलिटी भी चाहिए इसके अंदर। अच्छा, फर्स्ट में हमारे पास 12 केसेस बन रहे थे, सेकंड के अंदर 8 केसेस बन रहे हैं। सेकंड वाले में से देख लेते हैं कि ये कम केसेस है ना, इनमें से कोई फर्स्ट वाले में भी आ रहे हैं साथ। ये वाला केस तो नहीं आ रहा, बिकॉज इसमें वाइट किधर आ रहा है? इसमें वाइट आपका आ रहा है फर्स्ट बॉक्स के अंदर, जो इवेंट ए को सेटिस्फाई नहीं करता। राइट, इवेंट ए में एल या एम में हो सकता है सर। दूसरा केस आपके पास क्या है? दूसरे केस के अंदर जो ये वाला केस है, इसमें वाइट आपका कहीं भी आ सकता है बाकी सब। तो इसमें देखें आपके पास अगर इंटरसेक्शन वाले में एक केस क्या बनेगा, ए इंटरसेक्शन बी, जो दोनों को सेटिस्फाई करे। एक आपका ये बनेगा कि आर शुरू में आ जाए और आपके पास आ जाए फिर डब्ल्यू, और फिर बाकी दोनों जो मर्जी हो जाए, दैट डजंट मैटर। उनकी अरेंजमेंट्स कितनी हो सकती हैं? 2 फैक्टोरियल। आपके पास यहाँ पे हो जाएगा एक केस बन जाएगा येलो और ग्रीन, और फिर ग्रीन येलो। 2 केसेस आपके पास यहाँ से आ गए, ये दोनों को सेटिस्फाई करते हैं। एक और ये हो सकता है कि आर यहाँ पर आ जाए और फिर इधर आपके पास कुछ और आ जाए, और फिर वाइट यहाँ पर आ जाए और फिर इधर कुछ और आ जाए। ये कितने केसेस बन गए? ये भी 2 फैक्टोरियल केसेस बन गए। ये आपके पास टोटल आपके पास बन गए 4 केसेस। इसके अलावा कोई और पॉसिबिलिटी नहीं बनती है। तो प्रोबेबिलिटी ऑफ ए इंटरसेक्शन बी क्या हो जाएगा? इन का सम, प्रोबेबिलिटी ऑफ ए इंटरसेक्शन बी आपके पास आ गया 4 out of 24, which is 1/6. ठीक है, दिस इज ए इंटरसेक्शन बी। तो आपने वो तीनों प्रोबेबिलिटीज फिगर आउट कर ली। ए की प्रोबेबिलिटी इज 1/2, बी की प्रोबेबिलिटी इज 1/3, and A intersection B, this probability is 1/6. ठीक हो गया। अब ये तीनों प्रोबेबिलिटीज आ गई जो आपको चाहिए। अब आपको सिंपली क्या करना है, इस इक्वेशन के अंदर इनपुट करना है। देखिए आपके पास क्या आता है, प्रोबेबिलिटी ऑफ A इंटरसेक्शन B इक्वल्स प्रोबेबिलिटी ऑफ A इनटू प्रोबेबिलिटी ऑफ B। देखें ये इक्वेशन सेटिस्फाई होती है नहीं होती है। इंटरसेक्शन की प्रोबेबिलिटी क्या है? 1/6। प्रोबेबिलिटी ऑफ A is 1/2, प्रोबेबिलिटी ऑफ B is 1/3, and that gives you 1/6/1/6. Since these are equal, you say events are independent. A and B are independent. तो आपको ये तीनों प्रोबेबिलिटीज निकालनी थी, और फिर आपने ये देखना था कि उस इक्वेशन को सेटिस्फाई करते या नहीं करते। Now, that was a lot of working for 3 marks, but unfortunately that's how it is sometimes. ये आपने तीनों प्रोबेबिलिटीज निकाल के उनको इस इक्वेशन के अंदर इनपुट करना था। Question था। Question number 5, it says a game is played with an ordinary fair 6-sided die. A player throws the die once. If the result is 2, 3, 4, or 5, that result is the player's score. Okay. And the player does not throw the die again. If the result is 1 or 6, the player throws the die a second time, and the player's score is the sum of the 2 numbers from the 2 throws. Draw a fully labeled tree diagram to represent this information. Okay. Now, how do you do this? So let's try to break it down. It says there's a 6-sided die. How can we find the score of the person? The score is given by the number on the die if the number is between 2, 3, 4, or 5, okay, then that's the score. If that's not the number, if the result is 1 or 6, the player throws the die again, and then when whatever is the number on the second time, that is the score. Okay, so how is the tree diagram going to look like? The first time you have 6 possibilities. You can have 1, 2, 3, 4, 5, 6. What are the probabilities of getting each of these numbers? 1 over 6, 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 and 1 over 6. Now, if that person gets 2, 3, 4, or 5, the game stops there. The game does not go on, right? He does not throw a second die. But if he gets 1 or 6, he throws the die a second time. So he throws it again. The second time again, he has those 6 possibilities. He can get 1, 2, 3, 4, 5, or 6. What are the probabilities? 1 out of 6, 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 and 1 out of 6. And do the same thing for this last case as well, when he gets a 6 the first time. So yeah, he has these possible cases: 1, 2, 3. Let me make it slightly narrower. 2, 3, 4, 5, and 6. This is what the tree diagram would look like. It's quite some work for 2 marks, but this is what you could do here. All right. That's what the tree diagram looks like. These are all the possibilities that you could have. And these are the possible outcomes that you can have. Now, how is score calculated? They have told you about the score as well. In these, the score is 2, 3, 4, or 5. And in the cases where he gets 1 or 6 the first time, the score is the sum of the 2 numbers. So for instance, here, the score is going to be 6 plus 3. All right, that will be the score. Now let's move on to the second part. It says events A and B are defined as follows. Event A is that the player's score is 5, 6, 7, 8, or 9. And they say, find the probability of A. What's the probability that the score is 5, 6, 7, 8, or 9? Let's mark these scores. 5, this is one possibility. How else, where else can you get a score of 5, 6, 7, 8, and 9? If you get 1 the first time, the second time, if you get 4, the score becomes 5, right? 1 plus 4 is 5. And the second time, you could also get 5 because then the score would be 6. You could get 6 because then the score would be 7. So these are 3 cases that you get from this first part of the second step. And then similarly, you want 5, 6, 7, 8, or 9. So if you get 6 the first time, then the second time you could get a 1 because then the score would be 7. The second time you could get a 2, the score would be 8 in that case. And the second time you would get 3 as well, the score would be 9 in that case. And these are all the possibilities you could have that could give you a score between 5 and 9 with both 5 and 9 included. Is that okay? These are the only cases that we get here. There are no other possibilities. Now we can just find the probabilities of all of these cases and add them up together. Let's do that. So first of all, this is the easier one. Probability of 5, what's that? That's 1 over 6. Okay, or maybe just write them here. This is 1 over 6. So 1 over 6 plus, what about the other cases? This one is going to be 1 over 6 into 1 over 6. This number multiplied by this number. Right? That's 1 over 6 into 1 over 6. Now, all the other possibilities that I have here, this one, this one, this one, this one, and this one, they are basically all the same cases in the sense their probabilities are going to be the same. All of them have 1/6 into 1/6 probabilities. Okay, so what we can do is we can say we have 6 cases like these, and that could reduce our working a bit. We can say we have these 6 cases. All of them have this probability 1/6 into 1/6. So this is one case. When we get 5 from the first dice, then that is the score. That's 1/6 probability. Or we could get any one of these 6 cases. Probability of each of these 6 cases is 1/6 times 1/6. How many such cases do we have? 6. We multiply this by 6. Or we could also add this number 6 times. That's the same thing as multiplying it by 6. And that should give you the result. You can see what this is. 6 and 6 get cancelled. So we have 1/6 into 1/6, and that simplifies to 1/3. And that is what we were looking for. That's the probability that we wanted to show there. Is that okay? No problems? That's part B of this. Now it says, determine whether or not events A and B are independent. Remember the condition for independent events? 2 events A and B are independent if probability of A intersection B or A and B happening together, that's equal to probability of A multiplied by probability of B. This is the condition for 2 events being independent. So we need to find these 3 probabilities. Probability of A we have found already. Let's find the probability of B and see what that is going to be. B is the player has 2 throws. What's the probability of a player having 2 throws? The player gets 2 throws when he either gets 1 or 6. What's the probability of getting 1 or 6? Let's write that down here. Probability of B, which is that the player has 2 throws, that is going to be 1/6 plus 1/6, which is 1/3. Right? This case and this case, you just add them up together. 1/6 plus 1/6, that's 2/6, which is 1/3. That's the probability of B. Probability of A was also 1/3. We found that above. Both of these probabilities are the same. Now we need to think about the intersection. Probability of A intersection B. What's that probability? That is basically when both of these things happen together. When A is true and B is true. When both of these things are true. Now what's A? A is that the player's score is 5, 6, 8, or 9. 5, 6, 7, 8, or 9. And B is that he has 2 throws. When do you have both of these things happening? It's all of these cases. These 3 cases and these 3 cases, these are the cases when both of those things are happening together. Right? You have 2 throws, and the score is between 5 and 9. 5, 6, 7, 8, 9. Can you find this intersection probability? So we're talking about these cases. There are 6 such cases. Each of them has this probability. So we can say, we can say probability of A intersection B, that's going to be 1/6 into 1/6. That's one of those cases multiplied by 6, and that results in 1/6. So now we say, we've got probability of A intersection B. And on the other hand, we have probability of A multiplied by probability of B. Let's evaluate both of these and see what that gives us. Probability of intersection is 1/6. Probability of their product, probability of A into probability of B, what's that? That is 1/3 multiplied by 1/3. You get 1/6 and 1/9. These two are not equal to each other. So the condition for independent events is not met. So what do we say? These two events are not independent. They would be independent if this result turned out to be equal, but these probabilities are not equal, so they are not independent. Is that okay? Muslim, can you be specific in your question? What exactly do you want explained again? The intersection part? Okay. Intersection means A intersection B. It basically means probability of A and B both being true at the same time, right? A and B both being true at the same time. When are both of these things happening? That the score is this. I've highlighted them in yellow when the score is 6. And the player has 2 throws. So amongst those cases where the score is 5, 6, 7, 8, or 9, how many of them are coming when the player had 2 throws? This case was with 1 throw. That's not what we want. These cases were when we had 2 throws. So these that I've encircled here, these are the ones in which both of these conditions are met. That the score is from 5 to 9, and there are 2 throws. So that's the part where both conditions are met. That is what we call intersection. When both those things are true. This is the intersection part. Okay? So we just add all of these probabilities. One of these probabilities is 1/6 into 1/6. There are 6 such cases. We just add this 6 times, or we can just multiply it by 6 to get the same result. And that's exactly what we did here to find the probability of intersection. 1/6 into 1/6 into 1/6 multiplied by 6. And that's the intersection. And then we just compare these two sides. Since intersection probability is not the same as this probability, we say they're not independent. All right, that was part C of this question. Now it says find B given A complement. How do you understand this? Probability of B given A complement. Remember the formula for conditional probability? A given B is equal to probability of A intersection B divided by probability of B. Intersection means A and B both happening together. And in the denominator, you have what is given. Now they're saying find the probability of B given that A is not true. Let's use that conditional probability formula, and we say probability of B and A not being true. That's what you have in the numerator. In the denominator, you have the probability of A not being true, A complement. Okay. Now, what's the denominator? Probability of A complement. That's easier to figure out. Let's do that first. We know the probability of A is 1/3. What's the probability of not being A? So the probability of score not being one of these numbers, the total probability is always 1. So subtract from 1/3. That will give you the probability of A complement. So in the denominator, we just have 2/3. Right? Because probability of A complement will be 1 minus 1/3, which is 2/3. That's the denominator. Now, how do you find this? Where both of these things are true, that B is true and A is not true. Now, let's think about this. B is true and A is not true. Keep that in mind. The player has 2 throws, but the score is not one of these numbers. So it should be satisfying condition B, but not satisfying condition A. That's what it means. B and A complement. Okay? That condition B should be met and condition A should not be met. So which cases are we talking about now? When there are two throws, but the score is not one of these numbers. That's these cases or these cases. The probability of each one of these cases is 1/6 into 1/6. And there are 6 cases like this as well now. So you just multiply this by 6. Since you have to add this number 6 times, you can say that's the same thing as saying multiply this number by 6. And you would get your result from that. Let's see what this turns out to be. So we're considering this case and this case. Okay. What do you get for this? 1/6 into 1/6 for one of those cases. And then it has to be added 6 times. That's the same thing as saying multiplied by 6. Now let's simplify this. 6 and 6 get cancelled. And we get 1/6 divided by 2/3. And that's giving me 1/4. This is the probability that we were looking for. Let's have a look at question number 5 now. Eric has 3 coins. One of the coins is fair. The other 2 coins are each biased so that the probability of obtaining a head on any throw is 1/4, independently of all other throws. Okay, so there are 3 coins. One of them is fair. The other 2 are biased so that the probability of obtaining a head is 1/4. Eric throws all 3 coins at the same time. Events A and B are defined as follows. All 3 coins show the same result. At least one of the biased coins shows a head. Show that probability of B is equal to 7 out of 16. Now, how do you think of this? There are only 3 coins. Coins only have 2 possible outcomes. It's going to be easier if you just draw a tree diagram for this. And that will help you do this calculation quickly after that. So there are 3 coins. Let's say the first one is fair. Head, tails. These are 2 possibilities. And for the second one also has 2 possibilities, heads or tails, heads or tails. And the third one has 2 possibilities as well. This is what the tree diagram would look like. Now, what do we want? The event is that at least one of the biased coins shows a head. So what we're saying is the first coin, this one is fair. So this is 1/2 and 1/2. The other 2 are biased. And we want head on at least one of them. At least one of them. What are those cases going to be? Okay, so one possibility could be that we find all the cases where we have at least one head. It's going to be easier to think of it the other way around because that will be less number of cases. Let's find the probability of there being tails on both biased coins. Can we find this probability? Probability of getting tails on both biased coins? What would that be? In fact, in this case, it might even be easier to just forget about this first coin. So we'll keep this tree diagram. It will help us later when we are talking about all 3 coins at the same time. But in the first part, we're just talking about biased coins. So we could also just think of biased coins for now. These are the only 4 cases that we've got for biased coins. In that case, this is 1/4, this is 3/4, this is 1/4, this is 3/4, 1/4, 3/4. Okay, just think of the biased coin for now, because that's what we're talking about in event B. One of them needs to have a head. What we can do is we can find the probability of both being tails. What would that be? that will be 3 out of 4 into 3 out of 4. What's that? That's 9 out of 16. Probability of there being at least one H on biased points, what would that be then? 1 minus 9 over 16, that is 7 out of 16. Okay, this is one way of doing this. You could also just find this directly. You could say HH, HT, TH. Find the probabilities of all of them and then add them up together. Why would we multiply by 1 over 2? Are you saying for the fair coin? Well, you could do that. But then if you're looking at the bigger tree, you would say, you've got this case, this case, this case. You've got 3 cases here. Then you can multiply them by 1 over 2, and that's okay. But then you also have 3 cases here. You also add them up and multiply them by 1 over 2. Eventually, you get the same result as this. So when you have 2 separate cases, both of them multiplied by 1 over 2, eventually you get the same result. So we are saying, since we're not even talking about the fair coin for now, we can just simplify things a little and just focus on the biased coins, right? And just use this tree directly for that. Okay. You could use this bigger tree as well. That will give you the same result, but that's going to make things longer, more complicated. We don't have to do that. Okay. All right. So this gives you 7 out of 16. That's what we were looking for. Now in the second part, it says, find probability of A given B. This is a conditional probability. What is this equal to? Probability of A intersection B, or you can say A and B both happening together, divided by the probability of what is given. What's given? Probability of B, this is what is given. Now we already know the probability of B. We found that in the first part, that's 7 out of 16. We can have that in the denominator. Now, when are both of these events true at the same time? When A is true and B is true, when both of them are true. What's A? A is that all 3 coins show the same result. What are the 2 possibilities that we've got for that? H, 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 or tails, tails, tails. These are the 2 possibilities. Now, what's the intersection with there being at least one biased coin that shows a head? What's common between these 2 events? H, H, H is what is common. This is the common event because this will occur in both the events. It satisfies the condition for A and satisfies the condition for B as well. This is the only outcome that satisfies both of these conditions, that at least there is one head and all coins are showing the same result. So this is what you're going to get in the intersection in the numerator here. How do you find this probability now? H, H, H. That's 1 over 2 into heads was 3 over 4. Oh, sorry, 1 over 4 into 1 over 4. And that gives you 1 out of 32. That is what you would have in the numerator here, 1 over 32. And that should give you the result. You can see what the strength that would be. 1 out of 14, that's the probability that you get from this. You can write this in decimals as well and see what that turns out to be. 0.0714. That's the answer in decimals. Okay. Any problem with this? Part B? No? Okay, let's have a look at the next one now. It says the random variable X is the number of heads obtained when Eric throws the 3 coins. Draw up the probability distribution table for X for the number of heads obtained. Now you're throwing 3 coins. First of all, let's write down the possible values of x that you can get. So we make a table like this. In this table, in one row, you would have x. And in the other, you would have probability of x. What are the possible values of x? You could get 0 heads. It's possible that all of the coins show tails. You could have 1 head, 2 heads, and 3 heads. These are the 3 possible cases that you've got. Okay. What are their corresponding probabilities? 0 heads means you've got all tails. This. What would that be? Let's find that probability. Probability of there being all tails, that will be 1/2 into 3/4 into 3/4. What's that? 9 divided by 32, right? In decimals, that is 0, or you can just leave it like that, 9/32. That's the probability. We also know the probability of all heads. We calculated that earlier for the second part. That was 1/32, right? This probability, all heads. So 3 heads has this probability, 1/32. Okay. Subtract what from 1? No. 3 tails means 0 heads. Right? If we have 3 tails, that essentially means 0 heads. So this is the probability that we get 9/32. Why do we subtract it from 1? It's the same thing. If we say there are no heads, that essentially means there are 3 tails, right? So there's no need to subtract anything from 1 here. We already know the probability of 3 heads as well. That's 1/32. Now, what about the other 2 cases? Let's find one of them, and then we can find the rest by subtracting the remaining numbers from 1. So what's the probability of getting 1 head? Okay, when can we get 1 head? 1 head. What are the possible cases for that? One head, exactly 1 head. You could have head, tail, tail. You could have tail, head, tail, or you could have tail, tail, head. These are the 3 cases that you've got, right? When you have 1 head. Let's find the probabilities and add them up together. Now, what were the probabilities here? Let me just write them down. This was 1/4. This was 3/4. So write these that we need for now. 3/4. This was 1/4, 3/4, 1/4, 3/4. Okay, let's find these probabilities. This is 1/2 into 3/4 into 3/4. What's that? 9/32. And then this is 1/2 into 1/4 into 3/4. That will be 3/32. And then this one is 1/2 into 3/4 into 1/4. That's also 3/32. So probability of getting 1 head is basically sum of all of these numbers. Let's figure this out. Probability of getting all heads, we already calculated above. That was 1/32. Probability of getting 1 head, that basically means probability of head, tail, tail, plus probability of tail, head, tail, plus probability of tail, tail, head. These are the 3 probabilities that we have calculated above. Head, tail, 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 head, tail, and then tail, tail, head. Let's just add all of them up together. 9/32 plus 3/32 plus 3/32. And that gives us 15/32. Let's write that down as well. And now you can calculate this as well separately. If you want, you can find this case HHT, HTH, and then THH. You can do that. Or if you're sure about your first 3 calculations, you can just subtract from 1 all of these numbers. If you're sure about your earlier calculations, you can find the remaining one by subtracting these from 1. Let's see what that turns out to be. 1 minus, or in fact 32 minus 9 minus 15 minus 1, that's giving me 7. So the remaining number here turns out to be 7 over 32. Okay. So when you've calculated the rest of them, and there's only one left, and you're sure about the calculations that you've done until now, you can just subtract from 1 the rest of the probabilities to get that remaining number. And that's your final probability distribution table. 634 and 635, but 635 makes more sense because that's what we get when we round it off. Okay. All right, now let's look at the next one. So the next one that you've asked about is question number 6. Okay, let's try that. Question number 6 from this paper. Okay, Janice is playing a computer game. She has to complete level 1 and level 2 to finish the game. She's allowed at most 2 attempts at any level. For level 1, the probability that she completes it at the first attempt is 0.6. If she fails at her first attempt, the probability that she completes it at the second attempt is 0.3. If she completes level 1, she immediately moves on to level 2. Okay, that's a lot of information to process. Let's break it down and read it step by step. Okay, so she has to complete level 1 and level 2 to finish the game. There are 2 levels. She's allowed at most 2 attempts at any level. Okay, so for level 1 as well, she has 2 attempts. For level 2, she has 2 attempts. Okay. For level 1, the probability that she completes it at the first attempt is 0.6 for level 1. If she fails her first attempt, the probability that she completes at the second attempt is 0.3. If she completes level 1, she immediately moves on to level 2. Okay, for level 2, the probability that she completes it the first attempt is 0.4. If she fails at her first attempt, the probability that she completes it at the second attempt is 0.2. Show that the probability that she moves on to level 2 is 0.72. Now, how can she move on to the second level? She either completes the first level in the first attempt. What's the probability for that? 0.6, that she completes it on the first attempt. Or she completes the first level on the second attempt. In that case, we can say she fails the first attempt, that's 0.4. And then she is successful in the second attempt, that's 0.3. We multiply these two, and that should give us the result 0.6 plus 0.12, and that's 0.72. Now, it might make this easier if you draw a tree diagram first. That will make things a lot easier, okay? That will help you with the other parts of this question as well. So let's actually draw a tree diagram for this as well. They have not asked us to do that explicitly here, but if you do that once, that will help you with the rest of the calculations. Let's make a tree diagram for this. Let's do that in the second part. And that will make it, because we have more space here. Now, what are the possibilities? When she starts doing level 1, she either is successful in her first attempt or not successful. So let's say she either completes it or does not complete it. Or you can say, let's say she is successful or she fails the first time. Now, if the probability of her being successful the first time, that probability is 0.6. The probability of failure, therefore, would be 0.4. If she is successful at the first attempt, what happens? She moves on to the second level. And at the second level, she can either be successful or she can fail. Right? We'll talk about what happens afterwards in a moment. Let's consider this scenario, because here we are still at level 1. If she fails at level 1, on the second attempt, she can either be successful or she can fail. If she fails both attempts, the game ends there because she has only 2 attempts for each level. what are the probabilities associated with this one? For the second attempt, the probability of success is 0.3, and the probability of failure then would be 0.7. Let's actually stick to this for now. This is first level done. If she's here or here, she moves on to the second level. Now, in the second level, she has 2 attempts again. She can either be successful or she can fail in her first attempt. What are the probabilities of success and failure in the first attempt? In level 2, 0.4 and 0.6. This is 0.4 and this is 0.6. 0.4 and 0.6. If she is successful, the game stops there as well, right? She has completed both levels and the game finishes. If she fails at the second level once, she has another attempt. She can either be successful in that second attempt or fail in that second attempt. Again, here, she can either be successful in that second attempt or fail in that second attempt. What are the probabilities here? On the second attempt, probability of her being successful is 0.2, and the probability of her being her failing is 0.8. So we have 0.2 here and 0.8 here. This is what the tree diagram looks like. Now, let me actually color code it a bit so you can understand what is representing what level. So this is level 1. The blue part is level 1. And then the red part is level 2. Okay, blue part is level 1 and red part is level 2. Okay, now it says find the probability that she finishes the game. Finishing the game means that she completes both levels eventually. Now, what are the possible cases for that? She's successful here and successful again. She's successful the first time and then fails and then is successful. Or she fails the first time and then is successful and then is successful. She fails the first time, then is successful and then fails and then is again successful. These are 4 pathways that we've got. We find the probabilities for each of these paths and then add them up together. Okay, and that's going to give us the result. Let's see what this turns out to be. Let's look at the first path here. That's 0.6 into 0.4. Let me actually write that alongside here as well. The first part is that she's successful and successful. Then the second part, she's successful in the first level and then failed and then is successful. What's that probability? 0.6 into 0.6 into 0.2. And then the third part is fails, success, success. FSS. What's this? 0.4 into 0.3 into 0.4. And then finally, she fails and then is successful, then fails again, then again successful. And that gives us 0.4 into 0.3 into 0.6 into 0.2. So once you've made the tree diagram, it makes it quite straightforward after that. Okay, but making the tree diagram here was slightly tricky. That's the tricky part. Once you're done with that, the rest of it is not that complicated. And now you can evaluate this and see what that turns out to be. Okay, let's evaluate this. 0.6 into 0.4. Again, can somebody do this for me as well? To confirm this, 0.6 into 0.4 plus 0.6 into 0.6 into 0.2 plus 0.4, 0.3 into 0.4 plus 0.4 into 0.3 multiplied by 0.6 multiplied by 0.2. Yeah, so that's what I'm getting, 0.3744. That's the probability that we got for this 0.3744. And that's our final result for this part. Okay. And then it says, find the probability that she fails exactly one attempt given that she finishes the game. Now, what kind of probability is that? That is conditional probability. Okay, now how do we think about this? Probability, now that you have structured it well in the previous part, that would be very helpful for you in the last part now. Probability that she fails exactly one attempt, given that she finishes the game. That's the probability that we want to find out. Now, that's conditional probability. What's given is going to be the denominator. So in the denominator, you've got the probability that she finishes the game. And in the numerator, there's the probability that she fails exactly one attempt. And along with that, she finishes. Both of those conditions are true in the numerator. Now, do we know the denominator already? That's exactly what they made us find in the previous part. Probability that she finishes the game, that's 0.3744. That is going to be the denominator here. Now, what about the numerator? That she finishes the game, and while she finishes the game, she fails exactly one attempt. Now, look at these four cases that we had. Now, they're going to be helpful here for us since we wrote them down. In how many of these she's failing exactly one attempt? In the second case and in the third case. We just consider these two cases for the numerator here. Okay. Now, what are these two cases? Let me just evaluate these here separately. That will make things easier for the next part. 0.6 into 0.4. This is giving me 0.24, the first probability, and then 0.6 into 0.6 into 0.2. This was 0.072, and then the next one was 0.4 into 0.3 into 0.4, and this one is 0.048. And the final one, 0.4 into 0.3 into 0.6 into 0.2, that is 0.0144. These are the two cases that satisfy both criteria, that she's finishing the game and she's failing exactly one. That is what you would have in the numerator here. What's the total probability for those two cases? 0.072 plus 0.048. This is the total probability where both of these conditions are met. And that is going to give us the result 0.072 plus 0.048 divided by 0.3744. And that's giving me the conditional probability. That's 25/78. Or in decimals, that's 0.32051. Or we could say that's 3 to 1. That's the probability, the conditional probability that we were looking for. Okay, because that's otherwise that will be even longer. Finding the total number of cases, that takes even longer because you have to consider all possible cases for that. All right, makes sense. Let's move on to the next one because I'm running out of battery. My iPad is running out of battery, so we need to be a bit quick and do this last question quickly as well. Okay, it says Hannah buys 12 hollow chocolate eggs that each contain a sweet. Now, the eggs look identical, but she knows that 3 contain a red sweet, 4 contain an orange sweet, and 5 contain a yellow sweet. Each of her 3 children in turn randomly chooses and eats one of the eggs, keeping the sweet it contained. Okay. Find the probability that all eggs chosen contain the same color sweet. Okay, now how many are they selecting? There are 3 children, and they're randomly choosing. Yeah, in turn, they are choosing one of the eggs. What's the probability that they contain the same color sweet? Now, what are the possibilities? There are 3 different colors. We have red sweets, we have orange sweets, and we had We have yellow sweets. Now, all of them eat the same color sweet. That means they're all red. That is one possibility. Or they're all orange. That's another possibility. Or they're all yellow. These are the three possibilities that you have. Okay. Now, if they're all red, in how many ways can we do that? If they're all red, we could say the first one would have 3 out of 12, and then the second one would have probability of 2 out of 11, and then you have 1 out of 10, and then for the next one, for the O's, there are 4 orange sweets, so that's 4 out of 12 into 3 out of 11 into 2 out of 10, and then finally for yellow, it's 5 out of 12 into 4 out of 11 into 3 out of 10. So the first time a child takes a chocolate, the probability of it being red is 3 out of 12 when they have already taken a red chocolate out. For the next one, it's 2 out of 11 because there are 2 red chocolates left and the total number is 11 now, and then 1 out of 10. And similarly for the other ones as well, you just find these 3 cases and then you say it's either the first one or the second one or the third one. So you add add all of those cases up. Okay, you can see what that turns out to be. It's 6 over 110 into 12. That is 1320. 6 over 1320. Then you have 24 over 1320. And 60 over 1320. Add those cases and you'll get the result. What do you get from this? Three over 44. Okay. So that's the final result that we have, 3 over 44. And we get that by adding these cases up. All right, good. Let's move on. Now it says find the probability that all 3 eggs chosen contain a yellow sweet, given that all 3 children have the same colored sweet. Now what's given? Given is that they have the same color, and we have to find the probability that all of them have a yellow sweet, given that all are the same color. That's quite straightforward. Now we have those cases already from the first part. In the numerator, we want all yellow and same color. Now, of course, when all are yellow, they're also the same color. That's kind of obvious. In the denominator, you have the probability of what is given, the probability of being same color. That's the conditional probability formula, right? In the denominator, you have the probability of what is given. Given was all same color. We have found the probability of that already, 3 over 44 in the previous part. So that's your denominator here. Numerator is going to be probability of getting all yellow. That was 60 out of 1320. That's your numerator here, 60 out of 1320. And that should give you the result. Okay, what's this? Two over 3. Okay, thank you. So that's 2 over 3 or 0.667. If you want to write that in decimals, that's the result that we have. Okay, and then you have part C. It says find the probability that at least one of her children chooses an egg that contains an orange sweet. At least one of them chooses an egg that contains an orange sweet. At least one of them. Okay, so it could be one of them who chooses orange, 2 of them who choose orange, all of them choosing orange. It's going to be quicker if we subtract from the total the case where none of them chooses orange, right? Because, yeah, so that should make it simpler. At least one of the children choose an orange sweet. Okay, that's what they're saying. Now, what if we subtract from the total probability that all of them choose orange? Sorry, none of them choose orange, not all. none of them choose orange. And that will make this fairly quick, right? How do you find this? What's the probability that none of them choose orange? What was the what was the number of orange chocolates there or orange sweets there? That was 4 out of 12. So the total is 12. The number of orange chocolates is 4. And the remaining chocolates which are not orange, they are 12. What's the probability of none of them choosing orange? Probability of the first one not choosing orange, sorry. Yeah, the probability of first of them not choosing orange, that is 8 out of 12. Sorry, this is supposed to be 8 here. 8 out of 12. Probability of the first child not choosing an orange chocolate. And the second one also not choosing an orange chocolate, that will be 7 out of 11. And then the third one also not choosing an orange chocolate, that will be 6 out of 10. And you can see what this turns out to be. 1 minus 8 over 12 and 7 over 11 into 6 over 10. You can see what that is. 41 out of 55. That is this probability. 14 or 41? So I've got 2 conflicting answers here. Let me check this
So I
again.
didn't subtract it from 1.
Okay, 41 out of 55. Okay, good. So that's 41 out of 55. Let's look at this. Question number 6. Sajid is practicing for a long jump competition. He counts any jump that is longer than 6 meters as a success. Acha. Longer than 6 meters is a success. The probability that he has a success for this first jump is 0.2. Okay. यहाँ पे हम बना लेते हैं 3 jumps कर रहा है थोड़ा सा space चाहिए होगी हमें first jump could either be a success or a failure, right? Success की probability क्या है 0.2 failure की क्या होगी 0.8 Now for any subsequent jump the probability of a success is 0.3 if the previous jump was a success. Okay, so next time 0.3 probability होगी success की अगर previous time success थी and 0.1 otherwise यानी अगर पिछली jump पे failure था तो next time जो है वो 0.1 probability of success की so ये हमारे पास आ जाएगा 0.1 and this is going to be 0.9 ठीक है अच्छा and he makes 3 jumps तो अब इसके आगे उसको इस तरह कंटिन्यू कर लें बस यहाँ पर एक और jump होगी third jump either be a success or a failure success failure success failure you have success and failure this is what the tree diagram is going to look like इसकी probabilities आपको लिखनी पड़ेंगी अब success के बाद success की probability है 0.3 0.7 failure के बाद success की probability is 0.1 so that's 0.1 and 0.9 and similarly you have 0.3 0.7 here 0.1 and 0.9 here that is what your tree diagram is going to look like okay let's move on it says find the probability that Sajid has exactly 1 success given that he has at least 1 success okay now this is conditional probability given that आपके पास आ गया so you are given something उसको use करके आपने कोई probability निकालनी है remember conditional probability formula it looks like this it's not given in the formula sheet please make sure you remember this A intersection B divided by probability of B right so what that means is we are looking for probability of exactly 1 success probability of 1 success given that he has at least 1 success so we can say at least 1s that's what we are looking for Achha. Now what is this going to be equal to it's equal to probability of 1s intersection at least 1s divided by probability of at least 1s। ये आपने फिगर आउट करनी है, एक इंटरसेक्शन फिगर आउट करना है और एक नीचे वाली प्रोबेबिलिटी फिगर आउट करनी है, ठीक है। ओके, नाउ लेट्स figure this out. नहीं, ये वर्ड्स में लिखना जरूरी नहीं है, दिस इज जस्ट फॉर योर ओन अंडरस्टैंडिंग कि आपको पता हो कि आप क्या कर रहे हैं, ये लिखना जरूरी नहीं, आप डायरेक्टली कर सकते हैं, दैट्स परफेक्टली ओके। अच्छा, अब हम देखते हैं प्रोबेबिलिटी कैसे फिगर आउट करनी है, एटलीस्ट वन सक्सेस की प्रोबेबिलिटी। ये देखते हैं क्या आता है। एटलीस्ट वन सक्सेस का क्या मतलब है, वी कैन से अगर हम ये वाला केस माइनस कर दें वन में से, तो बाकी सारे केसेस में क्या होगा, एटलीस्ट वन टाइम तो सक्सेस आ रही होगी। So that's what we can do. We can say the total probability is 1. If we subtract from that the case when we have all failures, right? बाकी सारे cases में at least one success आ रही है, तो ये denominator तो हम इस तरह find कर लेंगे, ठीक है। So ये वाला case हम कैसे कर सकते हैं? This is the same as probability of all f's. And what is that going to be? 0.8 into 0.9 into 0.9. 0.8 into 0.9 into 0.9. What does that give you? 0.8 into 0.9 into 0.9, that is 0.648. ठीक है, ये आपके पास ये प्रोबेबिलिटी आ गई, डिनोमिनेटर आ गया आपके पास। नाउ इट सेज प्रोबेबिलिटी ऑफ एटलीस्ट वन सक्सेस इंटरसेक्शन वन सक्सेस। अच्छा, बेसिकली वन सक्सेस कहां पर आ रही है, एटलीस्ट वाला कंडीशन तो फिर ऑलरेडी मीट हो ही जाएगी ना, तो वन सक्सेस एग्जैक्टली कहां पर आ रही है वो आपको फिगर आउट करना है। वन सक्सेस किधर है, ये देखते हैं। यू कुड हैव S, F, F, that's one possibility. You could have failure, then success, failure. Then you could have failure, failure, success. These are the three cases that you have. Okay, that satisfy that condition जहाँ पे exactly one success आ रही है। ये हम यहीं पे evaluate कर लेते हैं, 0.2 into 0.7 into 0.9. This one is 0.8 into 0.1 into 0.3. And then you have 0.8 into 0.9 into 0.1. Now let's evaluate these numbers. 0.8 into 0.1 into 0.2 into 0.7 into 0.9. That is giving me 0.126. 0.8 into 0.1 into 0.3, that is 0.024. And then finally we have 0.8 into 0.9 into 0.1, that is 0.072. ठीक है, अच्छा, is that okay? Yes, thank you for that. ये हमने probability of failure निकाला है, so that's correct. ये हमने failures की probability निकाली है, तो अब at least one success की निकालनी थी, वो हमने निकाली नहीं, यहाँ पे वो add कर लें, यहाँ पे at least one s यहाँ पे add कर लेते हैं। ये हमने अभी 3s की निकाली है सर, at least one s, ये कितनी हो जाएगी, 1 minus 0.648. Let's see what that turns out to be. That's 0.352. ठीक है, वो भी हमने यहाँ पे निकाली नहीं थी, 0.352. दिस इज एटलीस्ट वन सक्सेस, ये हमें चाहिए थी, ये हमने फाइंड कर ली। दूसरा अब क्या है, वन सक्सेस वाली प्रोबेबिलिटी, ये आप साइड पे लिख लेते हैं, प्रोबेबिलिटी ऑफ वन सक्सेस ओनली। उन तीनों केसेस को ऐड कर लें, एस एफ एफ, एफ एस एफ एंड एफ एफ एस। ऑलराइट, सो 0.126 प्लस 0.024 plus 0.072. Let's add these three together and see what that gives us. Okay, so this is giving me 0.126 plus 0.024 plus 0.072. That seems to be ओके, ये कैलकुलेशन को दोबारा चेक कर लें. 0.8 into 0.1 into 0.3. I'm sorry, I'm doing a lot of careless errors today. Yeah. Okay, ये मैंने यहाँ पे भी गलत लिखा हुआ है. I'm sorry about that. This is 0.8, 0.1, and 0.7. This should have been 0.8 into 0.1 into 0.7. I wrote 0.3 there, unfortunately. Shoot. Let's do this and see what we get from this. 0.8 into 0.1 into 0.7, that is 0.056. Achha, 0.126 plus this and this. Okay, this turns out to be 0.254. Let's find that required probability now and see what that turns out to be. So that required probability, I'm not going to write that whole statement again. Numerator, ये क्या आ गया? जब one success आ रही है तो सब में at least one success तो हो ही रही है, तो वो intersection भी आपका ये होएगा. Numerator में आपके पास आ गया 0.254, denominator में at least one s वाला case, which is 0.35, ये भी 2 होना चाहिए था यहाँ पे. I think I need to go back to sleep and then do something again. This should have been 0.352 instead of 0.358. So this is 0.352 here. So 1 minus 0.648, this is 0.352 here. Okay, let's see what that turns out to be. This is giving me 0.7216. And that is what your final probability should be. Okay, all right. So that was part B. Let's look at the next one. It says, on another day, Sajid makes 6 jumps. All right. On another day, Sajid makes 6 jumps. Find the probability that only his first 3 jumps are successes or only his last 3 jumps are successes. There's an or between the two cases. Only his first 3 jumps are successes or only his last 3 jumps are successes. तो क्या cases हो सकते हैं आपके पास? First 3 jump successes हैं अगर, क्या मतलब है? Total 6 है, right? You could have success, success, success. It says only first 3 are successes. That means the last 3 are going to be failures. या तो ये हो सकता है, या फिर आपके पास दूसरा केस क्या हो सकता है? Last 3 are successes. That means first 3 are failures. So FFF into SS, for FFF and then SSS. These are the 2 cases that you have. Okay. अच्छा, आप देखें इसका जो ट्री डायग्राम होगा उसमें तो बहुत सारी ब्रांचेस आ जाएंगी. देखें पहले 2 होंगी, ठीक है, फिर 2 into 2 into 2, 2 raised to power 6. एंड पे जाके आपके पास ये कोई 64 ब्रांचेस बन जाएंगी. तो इट्स नॉट अ गुड आइडिया टू ड्रॉ दैट ट्री डायग्राम. बहुत ही लंबा हो जाएगा. You can figure this out without that. Okay. Usman, this is not binomial. We're not talking about कितनी सक्सेसेस आएंगी. इसमें एक सर्टेन, इसने एग्जैक्टली बताया हुआ कि फर्स्ट 3 सक्सेसेस होनी चाहिए, उसके बाद 3 फेलियर्स होने चाहिए, और फिर या फिर फर्स्ट 3 फेलियर्स होने चाहिए, उसके बाद सेकंड 3 सक्सेसेस होने चाहिए. इट्स नॉट बाइनोमियल. बाइनोमियल कली कंडीशन पे नहीं आता है, उनके तो स्पेसिफिक उसने सीक्वेंस दिया हुआ है. ऑलराइट, वी आर नॉट टॉकिंग अबाउट जस्ट द नंबर, वी आर टॉकिंग अबाउट अ स्पेसिफिक सीक्वेंस. तो ये आपको वैसे इवैल्यूएट करना पड़ेगा. ठीक है, या तो ट्री डायग्राम करके कर सकते थे, लेकिन वो बहुत लंबा हो जाता, और उसको डायरेक्टली वैसे सोचना पड़ेगा. नाउ थिंक अबाउट द कंडीशंस दैट आर गिवन. अगर देखें फर्स्ट टाइम क्या होता है, फर्स्ट टाइम तो उसकी सक्सेस की प्रोबेबिलिटी क्या है 0.2 और फेलियर की क्या है 0.8. तो इसमें जो फर्स्ट नंबर्स आपके पास आ रहे होंगे वो तो सिंपली यही होंगे. फर्स्ट सक्सेस की प्रोबेबिलिटी 0.2 और फर्स्ट फेलियर की प्रोबेबिलिटी जहां पर आएगी दैट इज 0.8। ठीक है, फर्स्ट टाइम तो हम यहाँ पे आ रहा होगा, लेकिन उसके बाद भी वो कंडीशंस है उसकी। क्या कंडीशंस है? अगर प्रीवियस जंप जो है वो सक्सेस थी तो नेक्स्ट सक्सेस की प्रोबेबिलिटी क्या है? 0.3। और अगर प्रीवियस जंप फेलियर थी तो नेक्स्ट सक्सेस की प्रोबेबिलिटी क्या होगी? 0.1 होगी। ओके, नाउ यू हैव टू कीप दैट इन माइंड। अब देखें, फर्स्ट सक्सेस थी तो नेक्स्ट सक्सेस की प्रोबेबिलिटी क्या होगी? बढ़ जाएगी 0.3, और नेक्स्ट की सक्सेस की प्रोबेबिलिटी इज अगेन 0.3। इसके बाद फेलियर शुरू हो गया, राइट? अब अगर प्रीवियस जंप सक्सेस थी तो नेक्स्ट में फेलियर की क्या प्रोबेबिलिटी होगी? सक्सेस के बाद सक्सेस की प्रोबेबिलिटी कितनी थी? 0.3 थी। सक्सेस के बाद फेलियर की प्रोबेबिलिटी क्या हो जाएगी फिर? 0.7। ओके, अब इस पॉइंट पे आप हैं यहाँ पे, अब फेलियर हुआ एक, फेलियर के बाद दोबारा फेलियर की प्रोबेबिलिटी, फेलियर के बाद सक्सेस की प्रोबेबिलिटी 0.1 है, तो फेलियर की प्रोबेबिलिटी क्या होगी? 0.9, and then again another 0.9. This is what you get for the first case. Okay, I hope that makes sense. Let's do the same thing for the second one now. First तो failure है, ये मैं पता है, ठीक है, उसकी probability 0.8 है. Now if the previous is a failure, what's the probability of the next being again a failure? That's 0.9, and then again 0.9. And now we are here. Failure के बाद success की probability वो तो कम हो गई थी, that was 0.1. ठीक है, लेकिन अब उससे next jump पर आएंगे, इस वाले पे प्रीवियस सक्सेस है, सक्सेस के बाद दोबारा से सक्सेस की प्रोबेबिलिटी कितनी है? 0.3. so this is 0.3 and the next one is again 0.3. this is what we get from this. ठीक है, ये दोनों प्रोबेबिलिटीज अलग अलग कैलकुलेट करेंगे, इनको ऐड कर लेंगे, and that's going to give you the result. Okay, 0.2 into 0.3 into 0.3 into 0.7 into 0.9 into 0.9. एक ये evaluate करना है आपको, ये देखते हैं क्या आता है. This is 0.0102, राइट? आगे 1 ही आता है, लेकिन इनफैक्ट ये 0 से स्टार्ट हो रहा है, तो आपको सिग्निफिकेंट फिगर ज्यादा रखने हैं. दिस इज 3 सिग्निफिकेंट फिगर्स, कैलकुलेशन में ज्यादा आपको चाहिए तो और लिखना आगे आगे आपको सारे 0.6. ओके, व्हाट अबाउट द सेकंड वन? ये इवैल्यूएट करें. 0.8 into 0.9 into 0.9 into 0.1 into 0.3 into 0.3, and that gives us 0.00582. Okay, you just add these two numbers, दोनों को add कर लें, देखें आपके पास क्या आता है. ठीक है, that's going to give you the total probability, and that turns out to be 0.016038, and that's your final answer. A contains 6 red and 4 blue. B contains X red and 9 blue. A ball is chosen at random from box A and placed in box B. The ball is then chosen at random from box B. Complete the tree diagram below given the remaining 4 probabilities in terms of X. Now, think about the situation first. You have 2 boxes. You have box A and box B. Box A, box B. How many balls does the first box have? 6 red and 4 blue. That's box A. You first have to take out a ball from box A. The probability of taking out a red ball is 6 out of 10. Probability of taking a blue ball is 4 out of 10. That's understandable. What about the second box? Box B has X red balls and 9 blue balls. Now, if you take out a red ball from the first box and put that in the second box, what's the number of red balls now in the second box? It's X plus 1, right? Because you took out 1 red ball from box A and put that here. The number of red balls in the second box will increase by 1. So it becomes X plus 1. So you have X plus 1 red balls in the second box now. What's the probability of taking out a red ball from the second box now? It's X plus 1 divided by, what's the total? x plus 1 plus 9, that is x plus 10. That's the total. So it's x plus 1 over x plus 10. What's the probability of taking out a blue ball in this case? That's 9 out of x plus 10. And then the second case. If you take out a blue ball the first time, if the first ball taken from box A is a blue ball, you had x red balls initially, they remain x. The number of blue balls increases by 1. The number of blue balls is now going to be 9 plus 1, that's 10 blue balls. The total is still x plus 10. So now the probability of selecting a red ball would be x over x plus 10. And the probability of selecting a blue ball would be 10 over x plus 10. That is what your tree diagram looks like in the first part. Okay. This is what you get. Now it says, show that the probability that both balls chosen are blue is 4 over x plus 10. Both chosen are blue. What does that mean? You have blue the first time and blue the second time. Just multiply those two. 4 over 10 into 10 over x plus 10. 10 and 10 get cancelled. And you have 4 over x plus 10. That's the second part. Fairly straightforward once you have the tree diagram there. Okay. And then part C of this, it's given that the probability that both balls chosen are blue is 1 over 6. Okay. Probability that both balls chosen are blue, that is 1 out of 6. That's the probability that we found in the previous part. They are saying that this probability was supposed to be 1 out of 6. Find the probability, correct 3 significant figures, that the ball chosen from box A is red, given that the ball chosen from box B is red. Now, using this, what you can actually do is you can find the value of x first of all, right? You know that the probability of getting 2 blue balls, that is 4 over x plus 10. And now they're saying that's actually equal to 1 out of 6. You get an equation from this that you can use to find the value of x. Let's cross multiply. It gives you 24 equals x plus 10, and the value of x turns out to be 14. So now you know the total the number of red balls in the second box is 14. Okay, so now it's something like this. Box A and box B. A had 6 red and 4 blue. Now B has 4 red and 9 blue. That's the starting, that's the initial stage, okay? All right, now find the probability that the ball chosen from box A is red. Probability that ball chosen from box A is red, I'm saying AR. You can say red ball from box A, RA, given that the ball chosen from box B is red. This is the probability that we want to find out. Now, what does that mean? In the denominator, you have the probability of what is given. What's given? That the probability that the ball chosen from box B is red. That is what is given. That's what you have in the denominator. In the numerator, you have the probability of both of those conditions being true, that the ball chosen from box A is red, and at the same time, the ball chosen from box B is also red. In the numerator, you want both conditions to be met, intersection of both of those cases. Now, what's the probability of the ball chosen from box B being red? The denominator. B can be red in either this case or this case. Okay. Now, what we can actually do is to make things simpler and not do calculations in terms of x. We can make another tree diagram. It's a but I'll just do it here again. That will make things a lot simpler for you. So make another tree diagram where you have the values input for x. You have red, blue, red, blue, red, blue. What was the probability for the first time? 6/10 and 4/10. The second time, for red, it was x plus 1/x+10. Now we know x is 14, x plus 1, that is 15/24. And then this would be 24 minus 15, that's 9/24. 9/14 plus 10, that's 9/24. And you have x/x+10, x is 14. So this is going to be 14/x plus 10, that's 24. And then the remaining would be 10/24. This is the tree diagram that you have now. What's the probability of getting a red ball from box B? Red ball from box B. I have to be more clear here, otherwise A and B are kind of using as well. Red ball from box A and red ball from box B, right? That's what we're saying. R and B are representing red and blue balls here, but these are representing the boxes, okay? A and B boxes. I hope that is clear, okay? What's the probability that you get a red ball from box B? This was the first box. This is box A and this is box B. Red ball from box B. That's this case or this case. What are the probabilities for them? Red, red or blue, red? That's the denominator. What would you have in the denominator? These two cases. 6/10 into 15/24. What does that give you? 6 into 15 divided by 240. That's giving me 3/8. And this one is 4/10 into 14/24. What does that give us? 4 into 14 divided by 240. And that's 7/30. The denominator is both of these cases. So in the denominator, we have 3/8 plus 7/30. This is the total probability of the ball from the second box, ball from box B being red, right? And then what about the numerator? Red ball from box A and red ball from box B. That's this case. Both red, 3/8. That is going to be your numerator. And that should give you the result. 3/8 divided by 3/8 plus 7/30. And that's giving me 45/73. That's the conditional probability that we were looking for. Make sense?